The main objective in this project is to propose a new type of impeller in order to compare and contrast this new design with the Russian impeller in terms of efficiency and shear rate. The process consists in three main parts: research, design, and simulation. The impellers can be seen here, the Russian and the sawtooth. We based our new design in the sawtooth impeller. Here is the cut of the new proposal of the impeller. It got 10 peaks in each face, 50 millimeters of diameter, and 10 millimeters of height. The impeller got the specifications in order to be compared with the Russian tank. In order to make the assembly, we extract the volume of the impeller in the internal tank. And finally, we obtain the cut ready to import to CFD as XT document. The mesh is very important in the simulations, so we select the polyhedral mesh to capture better the geometry, to get an homogeneous mesh and more accurate to face the flow calculation. Here it can be seen the mesh inversion, and if we go deeply, the Russian impeller have thinner cells in the impeller. Now it can be seen the mesh but in the sawtooth impeller, and also got cell thinner in the surface of the impeller. The most we select was the one that can be seen: the voltage plus, the gradients, the content density, the saturated flow, the k omega turbulence. For this analysis, we got three regimens: laminar, transition, and turbulent. In laminar, we got a Reynolds of 1, and if you can see, TKA stay very constant because there is not much turbulence. The simulation can be seen here. Now this is the laminar, also a Reynolds of 10, and the residuals, the TKA stay also constant. The velocity profile can be seen that in the corners of the impeller the velocity is the maximum speed. Here you can see more clearly the agitation of the radial form and the distribution of the speed. A non-dimensional wall distance for a wall-bounded flow, it depends of the friction velocity and the kinematic viscosity. So in the laminar flow, this has to be very small, like shown in the figure. This is the simulation for a Reynolds of 10. The residuals for a Reynolds of 100 in a transition regimes increases the speed, increases the shear rate, and the kinetic energy. In this case, the area around the impeller shaft acquires greater kinetic energy with the number of Reynolds. Here you can see the velocity profile and the velocity profile in colors in the tank. The voltage plus increases and as the number of Reynolds increases. And here's the simulation. Here is the transition Reynolds of 1000 and increases the kinetic energy. The velocity profile here in all the tank is greater, and the colors start to be more lively. In the images can be seen that the velocity in the whole tank is increasing. Also the voltage plus is increasing in the borders of the impeller. And here's the simulation for 1000. This turbulent, a Reynolds of 100,000, and their seed was established more or less, and it has a tendency every Reynolds is greater, so the velocity is greater, the velocity profile also, and the voltage plus is also in the maximum. There are some spaces that is the maximum voltage plus. In our scale, that is of 10. The simulation can be seen here. For a Reynolds, the highest, these are the residuals. Uh, Now it is possible to see that as the velocity increases, the kinetic energy of the turbulence, kinetic energy also. Since the model is made for turbulence, in this case the residuals established in the same range and the turbulence kinetic energy volume is maximum. Below you can see the profile of the turbulent kinetic energy. It is obvious that this increases with the velocity. So in the regions near the impeller have the greater kinetic energy, and this is distributed almost uniformly along the length of the tank. Here's the velocity profile, also the velocity profile, and the voltage plus is increasing. The simulation is over here. And we got the power number comparing to the theoretical. If you can see, they are almost the same with an error of 10%. The stress increase as the Reynolds increase, and that can be seen here. Although Russian impellers can be used for any type of single and multiple phases mixing dotty, they are more efficient for gas-liquid and liquid-liquid dispersion and provide high levels of shear and turbulence with lower pumping. With proper deflectors, these flows are converted into strong top-down flows above the below the impeller. Now the results for the Russian impeller are presented through different ranges: laminar, turbulent, and transition. This is the laminar for Reynolds 1 for the proposed impeller. The kinetic energy is very low, and the velocity profile can be seen that the tank is almost steady. Here it can be seen. The voltage plus is also in the minimum, and the simulation can be seen here. For laminar is Reynolds 10. This is the same tendency. I'm going to skip something. Here is the simulation. For a transition, we're going to skip to the simulation part. And you can see the tank is mixing and the velocity is increasing in all the tank. Now the maximum Reynolds number for transition regimen. Now the simulations for the turbulent regimen. And the comparison. There is the important part. If we can see the power number of the Rushton and the sawtooth in CFD are very similar, but the power number of the sawtooth is greater. And the stress of the proposed impeller have the same tendency. Also the shear rate increases, but the comparison, and we can see the theoretical, the CFD Russian and our sawtooth, you can be seen that the sawtooth is between both of them, the stress is very similar, and the shear rate, that is the most important, is greater. The sawtooth show a greater rate. So in conclusion, the geometry of the impeller is essential in the operation of an agitator. The design of the impeller provides higher TKA but lower velocity. Part numbers are pretty close for the new impeller version on literature. The shear rate of the sawtooth impeller is higher than the Russian impeller.